Okay, let's start then. I imagine you can see the slides, otherwise please tell me. We are arrived at the 6th lesson of this course. So we are beginning the second half of the course, which is made of 10 lessons. And today we will describe an important analytical technique, perhaps the most sophisticated among the ones we have discussed so far, which is the so-called method of steepest descent. And to give you the basic idea of the method, consider the integral here in the top part of this slide, where you can see there is a function of some parameter k, which will be studied in the limit when k is large. And the integral is a complex integral, so it's a contour integral along a certain path in the complex plane of the variable z, where the integrand is made of a function f of z and an exponential function. The parameter k occurs in the exponent, and it multiplies another function of the complex variable z, the phi function. The basic idea of the method is to use the machinery of analytic function theory, which allows us for deforming the contour, the integration path. And in particular, the idea is to deform the original integration path to a new contour, C prime, on which the function phi, the one that occurs in the exponent, has a constant imaginary part. So if you write the function phi of z, as you can see here, as a real part u plus j, an imaginary part v, then along the new contour of integration c prime, the imaginary part of the function phi, so v, must be equal to a constant. If this is true, then you can factor out the term containing the imaginary part v out of the integration sign. So you have the exponential e to j kv outside the integral. But more important, inside the integral now, what remains is the exponential with the real part, e to ku. And so, even though we are integrating in the complex plane, so along a curve, C prime, along this curve, by definition, this exponential function in the integrand is a real exponential. So we are in the same situation in which we find ourselves in the Laplace method, the method of asymptotically evaluating Laplace generalized Laplace type integrals. And so the idea is to enforce the rules of the Laplace method on the new contour. This is the nutshell of the idea of the method. Now, we will see in a moment that those paths on which the imaginary part v is constant are also simultaneously paths on which the real part u decreases or increases with the maximal rate. So if the decrease is maximal, we call this path a path of steepest descent, whereas if the increase is maximal, we will call the path a path of steepest ascent. The asymptotic evaluation in particular will make use of the former kind of path, so the path of steepest descent, hence the name of the method, the steepest descent method. Usually, those paths will go through some point, let's call it z0, characterized by the fact that the function phi is stationary at this point. So the first derivative of the function phi is equal to 0 when it is evaluated at the point z0. Now, this point is called a saddle point for the function u, for the reason we will see in a moment. So the shape of the function u in the vicinity of the point z0 of stationarity for the function phi is the shape of a saddle. So you can see along a direction you have a minimum, along another direction you have a maximum. So if you move from the stationary point along the curve for which the point is a minimum, you will describe a steepest ascent curve because you will increase your vertical abscissa. So the value of u will increase. Whereas on the opposite, if you move along the curve for which z0 is a maximum, then the value of u will decrease, and therefore you are on the steepest descent curve, which is the curve that is interesting for this asymptotic method. Now, let us try to see all these in more detail. So let us consider the analytic properties of the function phi, which I remind you is the function that occurs in the exponent of the exponential function. Let us make explicit the dependence of this function on the variable z, which is equal to x plus jy. So the real and imaginary parts, u and v, can be thought as real functions of the two real variables, x and y. And as we saw in the very first lesson of the course, the analyticity of the function phi is equivalent to requiring that a pair of partial differential equations of the first order hold the so-called Cauchy-Riemann equations, by which the partial derivative of u with respect to x is equal to the partial derivative of v with respect to y, and vice versa, the partial derivative of u with respect to y is equal to the partial derivative of v with respect to x, but in this case with a minus sign. Among the various consequences of the Cauchy-Riemann equations, we have, in this context, it is particularly important to note that at those points where the derivative of the function phi is different from 0, then if you calculate the gradients of the functions u and v, and I remind you that the direction of the gradient is the direction of maximal rate of variation of a function, and if you make the dot product of those gradients, then basically you need to calculate the sum of the products of the partial derivatives with respect to x and y. Now, if you enforce the Cauchy-Riemann equations, you will find that this algebraic sum is exactly equal to 0. So those gradients are geometrically two vectors that are orthogonal to each other. This means that the direction of maximum variation of u, which is the direction of its gradient, is orthogonal to the direction of maximum variation of v, which is, of course, the direction of its gradient. So this is the reason why the curves where the imaginary part v is constant are simultaneously also the paths where u varies most rapidly. And according to the direction that you choose along those curves, they can be named either steepest descent or steepest ascent paths. But there is even more. If you consider that u and v are harmonic functions, and this is something we already observed in the first lesson, that is, their Laplacian is equal to 0. And this is true again because of the Cauchy-Riemann equations, because in this case, as you can see here, you have the algebraic difference between the two mixed partial derivatives, and if the function is smooth, those mixed partial derivatives are equal by the Schwarz theorem. Then, for harmonic functions, we have a bunch of important properties, among which the maximum modulus theorem that we already stated for analytic functions of a complex variable, but there is a version of this maximum modulus theorem valid also for harmonic functions. The version is as follows. If u is an harmonic function inside an open connected domain D, then if you have a point with the subscript 0, where the function u has an absolute value which is larger than or equal to the absolute value of u at any other point xy inside the domain. So if you have a maximum, an absolute maximum for the absolute value of the function u in a certain point, then you must conclude that the function is equal to the maximum. So the function is a constant in the entire domain D. So if you have a harmonic function that is non-constant, so it's a non-trivial function, then a non-constant harmonic function inside an open domain cannot have maxima or minima, because it's easy to see that also minima are not possible. So this in turn means that if instead of considering, for example, an open domain you consider a closed domain, then the minima and the maxima of the absolute value of the function will occur exactly on the boundary, because they cannot be internal points. Now, geometrically, this means that if you consider the function u as a function of the two variables x and y, geometrically it is not possible to have neither a minimum nor a maximum. And so for this reason, the stationary points of u, that is, those points where the first partial derivatives are equal to 0, they must be saddle points, exactly of the kind we described before. So here, as you can see, there is neither an absolute minimum nor an absolute maximum, because depending on the direction that you choose on this surface, you can have either one, okay? So, and hence you have this typical saddle shape, okay? And for this reason, the method is also called the saddle point method. Now, in practice, sorry, in practice, what we need to do is to establish that the contour, the original integration contour of your function, can be deformed onto some steepest descent curve which passes through the saddle point or the saddle points, depending on how many of those you have. So let us discuss this in detail. Let us consider a point z0, which is by assumption a saddle point of order capital N. Now, letting small n be equal to capital N plus 1, this means that not only the first derivative is equal to 0 at that point for the function phi, but also a number of derivatives are equal to 0, the index m going from 1 to capital N. So if n, capital N, is equal to 1, we have only the first derivative equal to 0, and the second derivative, the next one, will be different from 0, and in particular equal to some complex, non-zero complex number in polar form a times the exponential of j alpha. And in this case, you have a simple saddle point, or a saddle point of first order. Otherwise, if capital N is larger than 1, you have a higher order saddle point, for which the first non-zero derivative is the one of order small n. Okay? Now, under this assumption, let us study the local behavior of the function phi in the vicinity of this saddle point. Let us agree to call the increment of the complex variable z minus z0 in this polar form to let it be equal to rho times the exponential of j theta. So rho gives us the distance between z and z0, and theta gives us the direction of the increment, okay? Then we can write, using the Taylor series, truncated to its first two non-zero terms, that the increment of the function phi, that is phi of z minus phi of z0, that can be approximated locally as 1 over the factorial of n times the nth power of the increment, z minus z0, times the complex derivative of the function phi with respect to z of order small n evaluated at the saddle point. That is, explicitly, by introducing the polar representation of the increment z minus z0, you have here rho to the nth power and the exponential e to j and theta, and also by inserting the representation of the partial derivative as a times the exponential e to j alpha, you can have, by grouping the two exponentials together, rho to the nth power times a divided by the factorial n, and then a unique exponential with the exponent being equal to j times alpha plus n theta. Or by exploiting the Euler's identity, the same thing, but in place of the exponential, now you see the cosine plus j sine functions of the real argument alpha plus n theta. Okay, with this expression in hand, now we are able to study the local behavior of the function phi in the vicinity of the saddle point. And in particular, since the directions of steepest descent are defined by the imaginary part of the increment phi of z minus phi of z0, here the minus is missing, I have to restore it, being equal to 0, because as we saw at the beginning, we require that the imaginary part of the function phi remains constant along those steepest descent or steepest ascent paths. Then we will require that the sine function, which is here in the imaginary part, be equal to 0. And in particular, if we wish that we are on a steepest descent path, we need to require that the function u, that is the real part, decreases away from the saddle point. So the real part, which is now the cosine function, as you can see here, the cosine function, that must be negative. If it were positive, you would not be on the steepest descent path, but you would be instead on the steepest ascent path, okay, which is also characterized by the sine function being equal to 0, but now the cosine function is instead positive. So, as a consequence, we see that the steepest descent directions are given by the angles theta of the increment equal to minus alpha divided by n plus an odd multiple of pi over n. Whereas the steepest ascent directions are minus alpha over n plus an integer multiple, an even integer multiple of pi over n. To give you an example, if you have a simple saddle point, so capital N is equal to 1, and therefore small n is equal to 2, and assume that the argument of the second derivative at the saddle point is equal to pi over 2, so alpha is equal to pi over 2, according to the equations you can see in the box, then the steepest descent directions will be equal to will be given by the angles theta equal to minus pi over 4 plus an odd integer multiple of pi over 2. So we have minus pi over 4 plus pi over 2, which is the direction here of the bisectrix of the first quadrant. Consider that the saddle point in this example is located at the origin, whereas the other path of steepest descent is opposite to this one, so it's the bisectrix of the third quadrant. You can see the arrows indicate the direction of descent. Okay, here you can help yourself by visualizing the saddle with this picture here. So if you move from the saddle to the steepest descent onto the steepest descent curve, you are moving here on the red line, on the green lines, whereas the red lines are the steepest ascent paths given by the directions minus pi over 4 plus even multiples of pi over 2. So there is alternating directions, steepest descent, steepest ascent, and so on. This is the typical pattern around saddle point. To give you some more examples, assume that your function phi is a polynomial of third degree, like z minus z to the third power over 3. If you calculate the first derivative, this is equal to 1 minus z squared, which can be factored as 1 plus z times 1 minus z. So the zeros of the first derivatives are the points plus or minus 1, and by definition, those are our saddle points. They are indicated here in the complex plane on the right. Now let us examine the order of those saddle points by calculating one more derivative. The second derivative at the point 1 is equal to minus 2. That is 2 times the exponential e to j pi. And this means, let me see if someone has arrived. Okay. Roberto has arrived. Okay. Buongiorno. I was examining the second derivative at the saddle point z equal to 1, and this is different from 0, so this is a simple saddle point, or a saddle point of order 1, where alpha, the argument of the second derivative, is equal to pi. As a consequence, the directions of steepest descent are along the angles 0 and pi, so the two arrows originating from the point 1 give you the directions of steepest descent. If you consider the other saddle at the point -1, at that point, the second derivative is equal to 2, which is a positive real number, therefore the argument is equal to 0, and therefore here alpha is equal to 0, and the directions of steepest descent are therefore vertical, as indicated here by the arrows in the picture. One more example. Take the function phi be equal to the hyperbolic sine of z minus z. Now, the first derivative will be the hyperbolic cosine of z minus 1, and if you equate this to 0, you will discover that you have an infinity of saddle points, which are the inverse hyperbolic cosines of the constant 1, that is, the numbers equal to 0 plus j 2m pi. So they are an infinite bunch of imaginary numbers equispaced along the imaginary axis with a period equal to 2 pi. The second derivative is, of course, equal to 0 at those points, because the second derivative would be the hyperbolic sine, which is equal to 0 at those locations. So we have we need to calculate also the third derivative. The third derivative is now the hyperbolic cosine, which is equal to 1 at the saddle points. So we have second order saddle points at each of those points, and alpha at those points is equal to 0. So by the rule examined in the previous slides, we have, for example, take the saddle point at the origin here. We have 3 directions of steepest descent, because now the saddle point is of order 2. It is not a simple saddle. So instead of having 2 directions of steepest descent, we have 3 of them, and they are equispaced. This is always so. So they point at angles which are 120 degrees spaced, okay? And of course, the bisectrices of those directions would be instead the directions of steepest ascent. Okay, so there is always a regular pattern in angle around the saddle point. Okay, so how does the Laplace method for complex contours work? So the saddle point method or the method of steepest descents. Here you can see the recipe in short. First, we need to establish that the contour, the original contour, can be deformed onto some steepest descent curve, which passes through some saddle point. And in order to accomplish this, you must be aware of the global geometry of your analytic functions, okay? Then usually the contribution near the saddle point gives the dominant asymptotic contribution, so what you need is to study what happens in the vicinity of the saddle point. Sometimes, however, the contour cannot be deformed onto a curve passing through the saddle point, and then in that case, the dominant contribution to the asymptotic evaluation comes from endpoints or singularities of the integrands. Sometimes, in addition, the deformation process introduces poles, because as you may remember, when you deform the integration contour from one contour to another, then it is possible by, if you recall the residue theorem, that you sweep across poles that may be in between the 2 contours. And sometimes those poles may lead to some significant contribution to the asymptotic evaluation. Sometimes it is even dominant. So we must be aware of the location of the singularities in the complex plane, because those singularities could be could have a role in the asymptotic evaluation. Now, let us consider the contribution of the saddle, which is usually the dominant one. Let us consider in particular a single path of steepest descent originating from a saddle point, z0, of order n-1, so small n-1. The dominant asymptotic contribution is the following that you can see in the box. Let us state precisely the assumption. C0, as I said, is a saddle point of order n-1. The function f occurring in the integral is locally of order z minus z0 to the exponent beta minus 1 in the vicinity of the saddle point. This is the assumption on the function f, which is stated also explicitly here. F of z is asymptotic to some constant f0 times the power of the increment z minus z0 with the exponent beta minus 1, where the real part of beta must be larger than 0. Otherwise, you would not be able to integrate your function because the singularity of the function f would be too high to allow the integral to be defined. As concerns the function phi, let us also state an assumption that concerns its local behavior. The assumption comes from the fact that we have a saddle point of order n-1. So the increment of the function phi is of the order z minus z0 to the nth power, as we already saw, with the factor 1 over n factorial and the nth derivative of the function phi at the saddle point. The latter derivative is the first non-zero derivative at the saddle point, and we will write it in polar form as an absolute value times the exponential with the phase alpha. Okay, then, if this holds, then the dominant asymptotic contribution of your integral I of k is given by the expression, the rather complicated looking expression here, which is, however, quite clear if you single out the occurrence of the large parameter k. The large parameter k occurs in two places. First of all, in the numerator inside an exponential function, which is the exponential function originally occurring inside the integral. However, now it is evaluated exactly at the saddle point, z0. The second point where you can see the large parameter k is in the denominator, where you can see it has an exponent, which is equal to beta divided by n. So it's a fraction whose numerator depends on the exponent beta, which describes the local behavior of the function f, and the denominator n describes instead the local behavior of the function phi. Everything else in this complicated expression is a bunch of numerical constants. So you have the constant f0, you have the factorial n of n to the same fraction beta over n, you have the exponential with the product beta times theta in the exponent divided by n, and you have the gamma function evaluated at the fraction beta over n. And also in the denominator, you have the absolute value of the nth partial derivative at the saddle point, which multiplies the large parameter k. What we have done is we have exploited the red curve you can see in this drawing that goes from the saddle point all the way down to somewhere. It's not important where you stop, because what matters is the neighborhood of the saddle point. So the integration limit at the bottom is not important asymptotically. Excuse me. Let us derive this result now, but let me drink first. Okay, the derivation is very similar to the derivation of the Laplace method. What we do is we change variable. So we introduce a new integration variable t, which is real and positive, by letting phi of z minus phi of z0 equal to minus t. So in this way, the exponential inside the integral becomes a real exponential, the Laplace type exponential, e to minus kt. Of course, in this process, we must change the differential, as you can see here in brackets. So this introduces here a denominator, phi prime of z. Okay, so now the integrand has this modified form, and we have factored out the exponential with k times the function phi of z0 outside of the integral. Now, near the saddle point, as we have already said, we can represent the increment of the function phi in terms of this quantity, which involves the nth power of the integrand of the increment z minus z0. So from this, you can deduce that the absolute value of this increment is equal to what you can see on the right-hand side, that is t to 1 over n, the factorial of n to 1 over n, and the absolute value of the nth partial derivative at the saddle point to 1 over n. So when you need to evaluate this ratio f of z divided by phi prime of z in a neighborhood of the saddle point, what you have is that in the numerator you will have the local behavior of f, which by assumption is one you can see here with the exponent beta minus 1. In the denominator, if you derive the function phi in the local, in the vicinity of the saddle point, you have this denominator here, in which you have the power n minus 1 of the increment z minus z0. Okay, now if you perform all the algebra, you will discover the expression here, in which you can see there are a number of terms, but there is also the angle theta. Since theta n plus alpha is equal to 2m plus 1 pi, then we have the result that we have stated in the previous expression for the dominant asymptotics of the function I of k, just by recalling what is the definition of the gamma function. This is the dominant term. What about the higher order asymptotic terms? Well, it is possible to derive also the higher order asymptotic terms, that is, to recover a full asymptotic expansion of our integral I of k. However, in order to do that, you must solve for z minus z0 in terms of a power series in the new integration variable t. That is, explicitly, z minus z0 must be written as a series of powers of the variable t with coefficients Cm to be determined. Now, from the definition of the new variable t in terms of phi, which can be written by factoring out a term like this, z minus z0 to the nth power, because we know the behavior, the local behavior of the function phi, and writing this function phi hat as a power series in z minus z0, where the function phi hat is analytic, close to the saddle point, then it is possible to invert this power series. So instead of having t as a function of a power series of z minus z0, to find the opposite, so z minus z0 in terms of a power series of t, by recursively solving z minus z0 as t to 1 over n divided by phi hat to 1 over n. This is quite tricky in practice, but it can be done in principle. At least we are sure that it can be done because of the implicit function theorem. In practice, on a case-by-case basis, the algebra can be more or less complicated, and we will see some example. An important observation is that everything we have said is based on Watson's lemma. This can be done by exercise, and since Watson's lemma is able to provide a complete asymptotic expansion with orders as high as one wishes, then the steepest descent method shares also this favorable property, and so it's able to provide a complete asymptotic expansion by using purely local information. So you need only to know what happens close to your saddle point. If you compare this with the stationary phase method, you will see a difference, because you could think to adopt an alternative strategy. So instead of deforming the integration path to a steepest descent path, you could consider a path on which the real part used is constant, and so the imaginary part varies most rapidly. So in this case, you have an oscillatory integrand instead of a decaying, an exponentially decaying integrand. And as we saw last lesson, when we discussed Fourier integrals, we also in the case of oscillatory integrals, you have the possibility of doing asymptotics, because the oscillations are a decay mechanism, because the oscillations cancel each other, unless you are in the vicinity of a stationary point, which in this case would be the saddle point. However, this decay mechanism is intrinsically weaker than the exponential decay mechanism that you find on the steepest descent path. And so, for this reason, if you adopt this strategy, you will be able to find the dominant asymptotic term, but you will not be able, in general, to find also the higher order terms. Okay? Having said that, our last observation is that in practice, it is not necessary to find exactly the shape of the steepest descent paths that go through a saddle point, because of the local nature of the method. So since what is important, what matters is a neighborhood of the saddle point, what's important is that you choose an integration path that locally is equivalent to a steepest descent path. away from the saddle point at distant points, it is also possible to allow for the integration contour to be different from a steepest descent path. In this way, you will, of course, introduce an error, but this error can be shown to be exponentially small with respect to the terms in your asymptotic expansion, and so it is negligible. Okay, so this is quite convenient in practice because you don't need to study exactly the shape of the curve. You need only to study its behavior in the vicinity of the saddle point. Let us apply everything to an explicit example just to give you the flavor of the method. The example is here in the box. You have the function I of the large parameter k as the integral, a real integral actually, from 0 to 1 with respect to the real variable t of the product of the logarithm of t times an exponential with a purely imaginary exponential e to j kt, okay, in the limit where k is large. Okay, first of all, you could try the stationary phase method because it's a real integral, it's a Fourier type integral. However, the difficulty is that the exponent function phi has a derivative which is equal to 1, and this derivative is therefore never 0. So there are no stationary points of the phase. So we cannot use the stationary phase approach. Then you could try integration by parts, which fails, however, because you are not able to evaluate the derivative of the logarithm, which is 1 over t, at the endpoint t equals 0, which is the endpoint, one of the endpoints of this integral. So we can try to introduce complex variables. So to consider the real variable t now as a complex variable z, and to use the steepest descent method. To do that, we must think now of the function phi as a function of z equal to jz. This is the function that multiplies k, the large parameter k, in the exponent. Okay, so it includes also the constant j now. And therefore, it's equal to jx minus y. If you calculate the first derivative of this function, the complex derivative, that's equal to j. And again, this is a constant different from 0, so we don't have saddle points. However, we can still find the steepest paths, because by definition, those paths are the paths where the imaginary part of the function phi is constant. And since the imaginary part of the function phi is equal to x from here, then we just need to enforce that x is equal to a constant. So this is the equation of a line in the xy plane, and in particular of a vertical line. So all the vertical lines where x is constant are curves where the imaginary part of phi is constant. And in particular, when y is larger than 0, so it's positive, then the real part of the function phi will be negative, and therefore those are steepest descent paths because the exponential decreases by increasing y. In contrast, if you have a negative y, then the real part of phi will be positive, and therefore you will have a steepest ascent path. So to perform the asymptotic evaluation, you need to run along vertical lines, x equal constant, on the positive side, in the upper half plane of the complex plane z, okay? And in particular, you can do that, consider that the original integration goes on the real axis from 0 to 1. Since the imaginary part of phi at 0 is different from the imaginary part of phi at 1, it is impossible to join those points with a single contour where the imaginary part of phi is constant, because as we have just seen, those contours are vertical lines. So the vertical line through the origin does not pass through the point 1, and vice versa. The vertical line through 1 does not pass through the origin. So how to proceed in this case? Well, we can use this trick. You can consider this rectangle here and use the contour formed by the vertical side C1, the horizontal upper side C2, and the vertical side on the right C3 that goes downwards. Okay, so we go from 0 to 1 through C1 plus C2 plus C3. C3, and this is what is written here as a complex integral that can be split into the contribution of the three sides, C1, C2, and C3, which are parameterized respectively by the real variable r that goes from 0 to capital R on C1, by the variable x on C2 that goes from 0 to 1, and again from the variable r that goes from 0 to r on C3 with a minus sign because the C3 part goes downwards. Now, if you let r tend to infinity, so you move the upper side, C2, to infinity, you will easily see that the exponential in the second integral goes to 0, so therefore the value of the second integral goes to 0, and what you remain with are the first and third integrals, which is what is written here at the bottom. Now, let us examine those two integrals separately. The first integral can be done in a closed form, so no asymptotics is needed, as you can see here, because if you change variable and you let s be equal to kr, the first integral can be written in this way as the sum of two contributions. The first contribution is available in a closed form here, and it's a logarithm of k over k. The second contribution does not contain the parameter k, it's a constant in the numerator. Here, the parameter k is in the denominator, and you can see the constant in the numerator is written in terms of this important mathematical constant, the Euler-Mascheroni constant, which is an irrational transcendent actually number. In the second integral, instead, we are not able to perform the integration analytically, but we can use Watson's lemma by developing in a power series the logarithm in the vicinity of the point 1. So we have this well-known power series representation, whose radius of convergence, by the way, is not infinite, it's equal to 1. However, we don't care about that because, as we saw, what matters is the behavior of the function in the neighborhood of the point 1 in this case. So we can extend integration all the way to infinity without introducing appreciable errors asymptotically. And so you end up with this expression in which you can see the first two terms come from the first integral, and the infinite summation here comes from the Watson's lemma applied to the second integral. And overall, you have a complete asymptotic expansion of your function I in terms of the large parameter k. Okay? Before going to a second example, I would maybe make a break because it's time to do that. So let's see in 10 minutes or so.
But what about the second part of the? There was another contribution, or I don't
Yeah.
know.
This one you are saying?
Yes.
Yes, this is what we have treated with Watson's lemma. So
Ah.
here you can see there is the logarithm of 1 plus JR. This is what we have developed with a Taylor series. And then we have used Watson's lemma to derive this term here in terms of
Okay.
inverse
I
powers of k. Okay?
Yes.
Okay, if you don't have any other question, we will see in 10 minutes. See you later. Okay, here we are again. I have a second example. Can you hear me? Ci siete, sì? Ok. Qualcuno che mi dica che mi sente, perché sennò non vado avanti. Ok, grazie. In this second example, we will perform the asymptotic evaluation of the Hankel function, which is important in wave phenomena because it expresses the fundamental solutions or Green's functions of waves in 2 dimensions. Now, the Hankel function, for example, of order Ni and second kind, h Ni1 of k, can be defined as a contour integral along the contour that you can see here, the green box, the contour C that goes from infinity in the upper half plane to infinity in the lower half plane, within the strip bounded by the abscissas minus pi and plus pi, and inside the integral you have the exponential to e to jk cosine z times the exponential j ni times z minus pi over 2. Ni is the order, and z is the integration variable. Now let us examine the existence of saddle points by evaluating the first derivative of the function phi, which in this case is equal to j times the cosine of z. So you look at the exponential where the large parameter k is present. If you perform the derivation, you will find minus j sine z. So we have the zeros of the sine function, an infinite number of them, which are simple zeros, because the second derivative, which is equal to minus j cosine, is different from 0 at all those points. So we have an infinite number of simple saddle points. For example, the origin of the complex plane is one of those saddle points. The second derivative at the origin, as at any other of those points, is equal to minus the exponential minus j pi over 2. Therefore, the quantity alpha is equal to minus pi over 2. And according to the rules we have derived for the directions theta of steepest descent, we will find that the directions are given by the angles 3 pi over 4 and 7 pi over 4. So 3 pi over 4 is equal to this direction here, the arrow C1 hat, and the other direction, 7 pi over 4, is in the fourth quadrant, the direction of C hat 2. Okay, the saddle point again is at the origin. Now, if you know that the integral along the original path C can be thought as the union of two parts going through the origin, one is given by C2 and the other part goes along C1 but with the opposite direction, then you can write the original integral as the integral along C2 minus the integral along C1. And then we can use the formulas for the method that we have derived before the break. For each of them, we have to use this formula. In one case, you will let theta be equal to 3 pi over 4 for C1. In the other case, for C2, you will let theta be equal to 7 pi over 4. The saddle point Z0 is at the origin. The exponent, the number n is equal to 2 because that's a simple saddle point. The value of the function phi at the saddle point is equal to j. The second derivative at the saddle point is equal to minus j. The exponent beta is equal to 1, and that's because if you look at the original integral, the function f of z is this exponential function here, which is analytic everywhere, and in particular in the neighborhood of the saddle point. So it tends to 1 when it tends to a constant when z tends to 0, and therefore the exponent beta must be equal to 1, because I remind you that beta describes the local behavior of the function f in the vicinity of the saddle point. So when beta is equal to 1, the exponent here, beta minus 1, is equal to 0. So therefore, this means that the function f is asymptotic to a constant in the vicinity of the saddle point, okay? This is why beta is equal to 1. And finally, this constant f0 has this specific value here. If you plug all those numbers inside the expression here, you will find the asymptotic expansion of the Hankel function valid to the lowest order, so the dominant asymptotic behavior of this Hankel function that goes as a term algebraic in k, 1 over the square root of k here, times an exponential term which contains k in the exponent, okay? But we can do even more. So we can go beyond the dominant term in order to find all the higher order terms. This requires a bit more pain. Let us first examine exactly the steepest descent and steepest ascent paths through the saddle point. They are, by definition, those curves where the imaginary part of phi is equal to the imaginary part of phi evaluated at the saddle point. And this is equivalent to the algebraic equation cosine x hyperbolic cosine y equal to 1. We can study this in the neighborhood of the origin by developing the cosine and hyperbolic cosine functions through their Taylor series, which are, of course, these ones. So locally, you can write the equation as an algebraic equation, y squared minus x squared equals 0, which can be factored immediately. The factor y plus x gives us the steepest descent path, because that's the equation of the bisectrix of the second and fourth quadrants. So it goes tangent to this steepest descent contour. Whereas the red factor gives us the steepest ascent path, which is instead the bisectrix of the first and third quadrants, and it's orthogonal to the steepest descent direction. When y in absolute value goes to infinity, then the cosine of x tends to 1/2 of the exponential of minus the absolute value of y, and therefore x tends to minus pi over 2 when y tends to plus infinity, and to plus pi over 2 when y tends to minus infinity. So the asymptotes of the steepest descent path go as in the picture here, and this is required in order to have the convergence of the integral. Okay, so it is possible actually to deform the original integration contour to this specific steepest descent contour, because they are both located inside the strip of convergence of the integrals. This just to be sure that the deformation that is required by the method is can be done. Now, the steepest descent path transformation, phi of z minus phi of 0 equal to minus t, becomes in this specific case j times cosine z minus 1 equal to minus t. And now in the neighborhood of the saddle point, that is the origin, you can develop the cosine through its Taylor series, and then you can write this representation, z squared over 2 factorial minus z to the 4th power over 4 factorial and so on. That's equal to minus jt, that is e to minus j pi over 2 times t. Now, the goal here is to invert this series. This is an expression that gives us t as a power series of z. We need the opposite. We need z as a power series of t. So what can we do? Well, we can leave the left-hand side, the first term here, the one with z squared, and bring everything else at the right-hand side. Then we take the square root in order to single out z. And what you obtain is that z is equal to the square root of 2 times e to minus j pi over 4 times the square root of t times an infinite summation, which comes from developing the square root in a Taylor series. However, this is not the goal because we have z both at the left-hand side and at the right-hand side. But now here we can bootstrap the method. So you can use this same expression here to insert it in place of z at the right-hand side. And if you do that iteratively, you will remove z from the right-hand side, and we will end up with a series that contains only the variable t. In particular, the exponents of t are 1 over 2, 3 over 2, 5 over 2, and so on. Once you have these, you can plug these into your integral, okay, that defines the Hankel function. And now, if you do that by developing also the exponential in a Taylor series, and consider also the differential, the change of variables from z to t, by performing some algebra, some very tedious and long algebra, you will be able to evaluate all those coefficients C0, C1, C3, and so on, C2, C3, and so on. And finally derive the complete asymptotic expansion of the Hankel function, which contains the dominant term with k over 1/2 in the denominator, but also all the higher order terms, so 1 over k, 1 over k to 3/2, and so on. Okay, so the derivation is tricky, the algebra is lengthy, but it's quite straightforward. What you need to do is to invert a power series. However, there is a simpler an alternative approach which is very commonly used in practice when one wishes to use the steepest descent method. And in the final part of this lesson, I will describe this alternative approach. This makes use of a different change of variables. So what we do now is to introduce a polynomial tau of a new variable s, such that tau of s is equal to the original function phi of z. So this is the original integral as an integral with respect to z. We change this to an integral with respect to s, which must be thought as a new complex variable. So we have an s-plane. In this s-plane, the integral involves the product of the exponential e to k tau of s, and this new function g, capital G, which contains the original function f, and includes also the derivative of z with respect to s, which comes from having changed variables, so it comes from the differential. Consider that this derivative, by the implicit function theorem, can be evaluated as a ratio of derivatives of tau and of phi with respect to their arguments. Okay. Now, the vicinity of the saddle point in the original complex plane of the z variable is chosen to correspond to the vicinity of the origin in this new complex plane of the s variable. So the saddle point is located at the origin in this new complex plane. Consider that the original path will be now some curve, let us call it p prime, that goes in the complex s-plane. It does not go through the saddle point necessarily, so we may need to perform a contour deformation in order to change the contour of integration to some steepest descent path. If we do that, it is possible that we run into singularities. Here you can see there is a pole singularity. Here you have a branch point singularity with the associated wiggly line, which is a branch cut. So you will need to take care of everything. In particular, if you sweep across a pole, you will find a residue contribution from that pole. If you sweep across the cut, well, actually, you cannot sweep across the cut because you would find a discontinuity. So what you need is to integrate along the two sides of the cut. So this cut will also give its own contribution to the process. But in the end, you will integrate along the steepest descent path. Now, assuming for the moment that the function g is regular close to the origin, which is our new saddle point, we may approximate this function g with its value at the origin. So you can take out this value from the integral. And what remains inside the integral is a canonical integral. We call it a comparison integral, which is the integral of a simple exponential function with a polynomial of s in the exponent. Now, how to choose this polynomial? this polynomial must be chosen in order that the real part of tau of S decreases most rapidly from the saddle point at the origin. Okay, hence the saddle point of this polynomial, which is the zero of its derivative, should be at the origin or close to the origin. The mapping derivative should remain finite near the origin, because we wish that our function g is regular and the function g contains this derivative inside. So the derivative must remain finite. So for this reason, the derivative tau prime of S must have the same order of 0 as the derivative of the original function phi with respect to z, because if this happens, in this ratio, you will not find problems and you will be able to evaluate this ratio in the neighborhood of the saddle point without finding singularities. The simplest polynomial tau that satisfies these requirements will yield, of course, the simplest comparison integral, and this will be our choice. Let us illustrate this considering again the same example, the Hankel function. This time we will proceed with the alternative approach. So the function phi, which is equal to j cosine of zeta, we already know that it has simple saddle points at an infinite number of points, and we consider explicitly the origin. Now we will equate this function phi to a polynomial tau of the variable s. Which polynomial? Well, the polynomial must be chosen such that the value of the function phi at the saddle point in the z-plane must be equal to the value of the polynomial tau at the saddle point in the s-plane, that is at the origin. And this value is equal to j. So as you can see, j minus s squared satisfies this requirement. So when z is equal to 0, the function phi is equal to j, and when s is equal to 0, the function tau is also equal to j. Okay, so there is matching of the values at the saddle point. In addition to that, if you calculate the first derivative of tau, which is equal to minus 2s, the second derivative being equal to minus 2, then you see that s equals 0 is a simple 0 of tau. So it has the same order of the saddle point as a 0 of the function phi. Why is this important? Well, because now we can evaluate this derivative, dz over ds, as a ratio of derivatives. Since both of those terms in the numerator and the denominator go to 0, when s tends to 0, we may apply the rule of the L'Hopital and proceed by differentiating both the numerator and the denominator. The numerator, therefore, becomes the second derivative of tau evaluated at the saddle point. In the denominator, we perform the second derivative. However, we are differentiating with respect to s, so we consider z as an intermediate variable. So we first differentiate with respect to z, and we get the second derivative of phi times the derivative of z with respect to s in the limit when s tends to 0. Now, the latter term is exactly equal to the left-hand side that we are wishing to evaluate. So if you take this term from the denominator to the left-hand side, you will find the derivative of z with respect to s to the second power. So you just need to take a square root to get the value, the asymptotic value of this derivative. That's the square root of the second derivative of tau at the origin divided by the second derivative of phi at the saddle point. We have already evaluated those numbers. They are respectively minus 2 and minus j. So it turns out that this term here is equal to the square root of 2 times the exponential of j times minus pi over 4 plus an integer multiple of pi. When this integer is even, we get the steepest descent directions that we are interested into. Okay? So to conclude, our function g, which is the product of f and the derivative we have just considered, at the origin, that is at the saddle point in the s-plane, is equal to the value of f at the saddle point times this number we have just calculated. And so it has this specific value here. It's a constant, okay? What can we do with this constant? Well, we take the original integral in the z-plane, we change variables in the s-plane, we approximate the function g with its value at the origin, which is the constant we have just calculated. It's written here in purple, and it's taken outside the integral. The integral now involves only the exponential function with the polynomial j minus s squared in the exponent. Now, this exponential can be split. There is an exponential that does not depend on s, e to jk, and that goes also outside the integral. Finally, we remain with the standard Gaussian integral, the exponential minus ks squared, for which we know the value in analytic closed form. The value is the square root of pi divided by k. So if you plug this into the expression, you will recover the dominant asymptotics of the Hankel function that we already obtained with the previous approach. And also in this case, you can recover the complete asymptotic expansion. What you need is just to represent the function g of s in terms of its Taylor series. Here we have considered only the lowest order term of its Taylor series, so the value of the function at the saddle point, but you can instead expand the function g through its Taylor series by retaining all its terms, that is, all the powers of s. If you do that, you can bring the summation outside the integral together with the constants. Inside the integral, you will remain with the powers of s. And also this kind of integral, a modified Gaussian integral, can be evaluated in a closed form. You can try by yourself. This can be evaluated by successively differentiating a Gaussian integral, and it turns out that if n is odd, the value is equal to 0. If n is even, the value is the one given here as a certain derivative of the quantity square root of pi over k. So again, we have in the end the complete asymptotic expansion of the Hankel function, because in the end we have a power series in terms of inverse powers of the large parameter, where you can see the dominant term is the one with 1 over k to 1/2, and the next terms give you the next orders, k to 3/2, and so on. Consider that the goal of this second approach is to find the right polynomial tau such that this ratio remains finite. Now, it may happen that the function f has singularities close to the saddle point gs, and in that case, of course, the function g will also have correspondingly singularities near the saddle point at the origin. If this occurs, these singularities must be isolated in the simplest form, and then it will be required to introduce a new class of comparison integrals. Now we will see some examples. Let us give some cases that you can find in practice. The first case is the one we have discussed so far. So you have just a single saddle point at the point ZS. Now we will consider the possibility that it is a higher order saddle point, so a general order m. When m is equal to 1, we have a simple saddle point. And in addition, f is regular close to the saddle point. Then the right polynomial to be used in the second approach is this one, a constant, which is the value of f of phi at the saddle point, minus a monomial s to m plus 1. Okay? With this kind of change of variables, you end up with this comparison integral, which is the integral of an exponential again, e to minus k s to m plus 1. This is a canonical integral which can be evaluated analytically, and it displays an algebraic dependence on k. As you can see here, I have reported the closed form evaluation of the integral, and here you can see there is the k parameter with the exponent 1 over m plus 1. So you have an algebraic dependence on the large parameter k. Okay. This is of course only the dominant asymptotic term, because we have considered the lowest order term in the Taylor development of the function g. But in principle, you could go beyond and consider also the higher order terms. A second case is when you have two saddle points, not only one, z1 and z2, both are simple, so they are of order 1. However, those two saddle points can come arbitrarily close to each other. So depending on some additional parameter, sigma, say, those saddle points may coalesce, so they can come arbitrarily close to each other. Now, in this case, it is useful to introduce a polynomial of this kind, a0 plus sigma s minus s to the third power over 3. In this way, the two saddle points are mapped onto the two numbers plus or minus the square root of sigma in the S-plane. Those are the two saddle points in the S-plane. And as you can see, when sigma goes to 0, those two numbers coalesce onto the origin. So the origin becomes a saddle point of order 2 in the limit. Now, if you insert this polynomial inside your integral, and you perform suitable change of variables, you will end up with the new canonical integral, the one in red here, which is expressible in terms of special functions known as the Airy functions. Now, it turns out that if you are interested in studying, for example, the phenomenon of the rainbow, well, the phenomenon of the rainbow involves exactly this mathematics. So it involves two saddle points which may come arbitrarily close to each other. So therefore, this kind of integral is also called the rainbow integral, and the Airy functions are also called the rainbow functions. Another case is that of three saddle points, again, simple saddle points. In this case, we will introduce a polynomial of fourth order, whose first derivative has zeros, and therefore there are saddle points now at three locations in the complex plane. One is the origin, and the other two are plus or minus j, the square root of a. As you can see, when the parameter a goes to 0, the two saddle points removed from the origin tend to go close to the origin, and therefore in the limit you would have a third order saddle point at the origin. If you insert this polynomial inside the integral, after changing variables, you will end up with a new canonical integral, the one in red, that requires, in order to be evaluated, the introduction of another family of special functions different from the Airy functions. In particular, they are called the parabolic cylinder function of order -1/2. Of course, those functions are very well studied as the Airy functions. They are tabulated, and so we are able to evaluate them analytically and numerically. Another important case is that of a single saddle point of order 1, however, with a function f which has a singularity in the form of a pole, a simple or multiple pole, at some location z, p, which can come arbitrarily close to the saddle point. What's the problem of a pole close to the saddle point? Well, the problem is the following, that if you have a pole close to the saddle point, then the radius of convergence of the Taylor series, which represents your function g with initial point at the saddle point, cannot be larger than the distance between the saddle point and the pole. So if the pole comes arbitrarily close to the saddle point, this radius of convergence goes to 0. So the circle of convergence shrinks to 0. This implies that the asymptotics will become worse and worse in quality, unless you do what is described here in the box. That is, you isolate the singularity in this term here, which contains the pole. The pole is at s equal b, because that's the 0 of the denominator. So this is the problem, the term that causes the problem. And then there is another addend, which is instead regular, so it does not display the pole singularity. For the latter term, you proceed as usual. So you will find the usual asymptotic evaluation in terms of the inverse power of k to 1/2. Then there is the singular term, which needs the introduction of a new canonical integral. And again, this canonical integral can be expressed analytically in terms of special functions. The special function in question is the error function, also called Fresnel integral. So this is, for example, the situation that occurs if you try to describe the transition between light and shadow. So the light, the lit part of space corresponds to having a pole. That pole crosses the steepest descent path in the vicinity of a saddle point when you go to the shadow. So the transition from light to shadow is described in terms of the error function or the Fresnel integral. There is a transition region, actually, since you don't have a discontinuity, so you don't go from full light to full shadow, but there is a narrow transition region in which you cross the shadow boundary, and in which the light intensity progressively decreases. The extent of this region is smaller and smaller as frequency is increased. So if the parameter k is frequency, if you consider high frequencies, then the region of transition will shrink around the shadow boundary. In any case, this was just to mention this kind of asymptotics occurs in this practical problem, which is a diffraction problem, of course. Okay, we are finished for today. What I've told you today can be found in the book by Ablowitz and Focus, I already mentioned. And as concerns the second approach to the steepest descent method, that is beautifully described in chapter 4 of this book by Felsen and Markowitz, which is a classical book on radiation and scattering of waves. That's a difficult book. It's not easy to read, but it contains almost everything can be done in diffraction problems. So it's something that at least once in your life you should take a look at. Okay, thank you for your attention. If you have questions, I'm here. Otherwise, we will meet on next Tuesday. I hope to be able to be there in presence for those who are in the department, but I will let you know on Monday how we will do the lesson. Okay. Thank you again, and see you.
Thank you. Bye.
Thank you. Bye-bye.